Welcome back to the deep dive. Today, we're doing something a little bit different. We're stripping away the macro world. So forget the tables, the chairs, the solid steel beams you see around you, and we are going strictly microscopic.
Right, way down to the atomic level.
Exactly, because we're looking at a simulation today that tries to answer a really fundamental question in material science, which is how do atoms actually move through a solid crystal?
And it's a question that sounds kind of counterintuitive on the surface, right? Because we define solids by their rigidity. But if you look closely enough, like really closely at that atomic scale, rigid is just the wrong word entirely.
Yeah, it's a chaotic dance down there.
It really is. It's dynamic, it's stochastic, and understanding that chaotic movement, specifically diffusion, that's how we engineer literally everything from semiconductors in your phone to, you know, jet engine turbine blades.
Right. And usually when we talk about diffusion on this deep dive, we're talking about gradients, like a drop of food coloring in water, high concentration flowing to low concentration.
Classic example, yeah.
But the source material we have today, which is this really fascinating technical lecture on computational materials engineering, it focuses on a Monte Carlo simulation of vacancy hopping, and it strips even that gradient away.
Exactly. What we're looking at today is an experiment in self-diffusion. So, there is no chemical gradient pushing things. There is no external force. It is purely thermal energy and, well, probability.
Our mission today is to demystify this, to figure out how scientists use literal random numbers, the Monte Carlo part of it, to predict exactly how fast atoms diffuse through a material, even when the system is just sitting there in equilibrium.
And that's the magic of it. You have this chaotic movement happening under the hood, and we can actually quantify it.
So let's set the stage for you. The source walks us through this Python-based simulation, and they use one-dimensional lattice. Let's visualize that first.
Sure. So imagine a single line of atomic sites. The easiest way to picture it is like a really long row of seats in a movie theater.
Okay, I like that. So the atoms are the people sitting in the seats.
Right. And in this 1D theater row, almost all the seats are taken, but not every single one. There are a few empty seats, and those empty seats are the vacancies.
And the simulation specifically tracks these vacancies, right? Because if every single seat in the row is full, nobody can move. You're just stuck next to the guy eating popcorn.
Gridlock. Complete gridlock. Atoms can't move if there's no space to move into. The vacancy is the enabler here.
So if I'm an atom and there's an empty seat to my right, I can hop into it. But when I do that, my old seat is now the empty one.
Is now the vacancy, exactly. So when the atom moves one way, the vacancy effectively moves the other way. By tracking the empty seats, we're actually tracking the potential for movement.
Okay, that makes perfect sense. Now, looking at the setup parameters fed into this computer simulation, there are a few numbers I want to unpack because they really make this realistic. First, the vacancies. The simulation sets up a system with 1,000 available vacancies.
Right, which, to be clear, is a massive exaggeration.
Yeah, I was going to say,
Yeah.
in a real piece of copper or something, are there really that many empty spots all grouped together?
Definitely not. In a real material at equilibrium, vacancies are defects. They are incredibly rare. You might have one empty site in a million, or even one in 10 billion, depending on the metal and the temperature.
So why pump the simulation full of 1,000 of them?
It's a standard trick in computational materials engineering. If you modeled a real crystal with realistic, super low vacancy counts, you'd have to run the computer simulation for, I don't know, years.
Just waiting for one atom to happen to be next to an empty spot.
Exactly, just to get enough jumps for statistically significant data. By flooding the system with vacancies, they increase the frequency of the events. It lets them calculate a diffusion coefficient in seconds rather than centuries.
Scale it up to measure the rate, then normalize it later.
Got it.
And to get that data, they run it for 10,000 attempts, or time steps.
Yeah, 10,000 steps gives the algorithm plenty of chances to roll the dice and see what happens.
Speaking of rolling the dice, let's turn the engine on. The environment for this simulation is set to 1,000 Kelvin.
Scorching hot.
Yeah, that's over 700 degrees Celsius. And the other parameter is the migration energy, represented by E sub m, which is set at 1.2 electron volts, or EV.
Those two numbers are the absolute core of the physics here.
Let's break that down, because I really want you, the listener, to grasp this relationship. The migration energy, the 1.2 EV, that's the barrier, right?
Think of it as a hill. It's the physical energy barrier the atom has to overcome to squeeze past its neighbors and hop into that empty seat. It takes actual work.
And the temperature, the 1,000 Kelvin, That provides the fuel to get over the hill.
Precisely. Temperature is just a measure of the average chaos, the thermal vibrations in the system. At room temperature, an atom might only have, say, 0.025 eV of thermal energy.
Which is practically nothing compared to the 1.2 EV hill it needs to climb.
Right. It's trying to jump a 10-foot wall with a 2-inch vertical leap. The probability of making it over is astronomically low, which is why the desk you're sitting at isn't just spontaneously melting into a puddle.
The atoms are locked in.
Yeah.
But when we crank the heat to 1,000 Kelvin in the simulation,
The thermal energy increases massively. Now, it doesn't mean every single atom suddenly has 1.2 eV, but the distribution of energy widens out. Statistically, there will be some lucky atoms that momentarily gather enough thermal kick to vault over that wall.
okay, so this brings us to the rules of the game. We've got the heat, we've got the burial. How does the computer actually decide who gets to jump?
This is where we calculate the jump probability, or p-jump.
And the formula they use in the lecture involves that migration energy and the temperature, right?
Yes, it's an exponential function. Basically, the probability equals the exponential of negative EM divided by Boltzmann's constant times temperature.
I don't want to get us too bogged down on the math, but the fact that it's exponential is a huge deal, isn't it?
It's everything. Because it's an exponential decay function, the system is incredibly sensitive. If you drop the temperature by just 10%, the probability of jumping doesn't drop by 10%. It plummets. It might drop by a factor of 100.
Wow. Okay, so at 1,000 Kelvin, the math spits out a specific jump probability. Let's just say, for example, it comes out to 0.2, a 20% chance.
Sure, let's use 20%. So the computer looks at an atom next to a vacancy and says, okay, you have a 20% chance of having enough energy to jump right now.
And here is the actual Monte Carlo part, the dice roll. I love this concept.
Walk us through it.
So instead of simulating every single microscopic vibration of the atom, which would take forever, the computer just generates a random number between 0 and 1.
Purely random.
Right. And if that random number is less than our jump probability, so less than 0.2, the jump is approved. The atom moves.
And if the random number is higher, like 0.8,
The jump is rejected.
Yeah.
The atom stays put. It's so elegant.
it really is. It perfectly mimics nature without doing all the heavy computational lifting. Because in nature, even if an atom is really hot, it doesn't move every single time it vibrates. It mostly just jiggles in place until a random lucky fluctuation pushes it over the edge.
So the Monte Carlo random number generator is just a shortcut for the chaos of thermal vibrations.
Exactly. It saves us from having to calculate force equals mass times acceleration for trillions of useless little jiggles.
Okay, so the computer rolls the dice. It gets a 0.1. The jump is approved.
Yeah.
We have action.
We have action. But now the question is, where does it go?
Right, because we are in this 1D lattice, this single row of theater seats. So there are only two choices, left or right, -1 or +1.
And remember, there is no concentration gradient. There's no wind blowing these atoms, no magnetic field dragging them. So how does it choose?
A coin toss.
A literal 50-50 coin toss.
Right.
Another random number decides the direction.
Which creates what physicists call the random walk. And I want to pause on this because if you're listening to this and picturing a random walk, it sounds completely aimless.
It is aimless.
Right. If I take a step to my left and then a step to my right, I'm right back where I started. If these atoms are just shuffling back and forth randomly over 10,000 attempts, how do we get actual diffusion out of that?
That is the great paradox of the random walk. You are totally right. On average, the displacement is 0. If you simulate 1,000 atoms starting at position 0 and you let them walk randomly for an hour, their average position will still be 0.
Because the lefts and rights cancel each other out.
Exactly.
So how do the scientists measure progress in the simulation? How do we score this?
We have to stop looking at the average position and start looking at the spread. We want to know how far they have wandered from their origin, regardless of which direction they went.
And mathematically, the trick to doing that is squaring the distance.
Yes. The mean square difference, or MSD, sometimes called mean square displacement.
Okay, so if an atom moves left to -1, -1 squared is +1.
Right. And if it moves right to +1, +1 squared is also +1.
So by squaring it, we get rid of the negative signs. Every single step, no matter the direction, contributes to the magnitude of the spread.
You nailed it. We stop caring about direction and we only care about magnitude. And the simulation tracks this MSD value across all 10,000 steps.
And in a standard diffusion process, like the one we're modeling, what does that look like on a graph?
It's beautiful, really. The mean square displacement grows linearly with time. If you put MSD on the y-axis and time on the x-axis, you get a straight upward sloping line.
Which brings us to Einstein, actually.
It does. This was his famous contribution to Brownian motion back in 1905. He proved that this linear relationship between the squared displacement and time is the signature of random diffusion.
So the slope of that line on the graph.
That slope is the gold. That is what gives us the effective diffusion coefficient, the D effective.
Let's give them the grand calculation. The formula the source uses is D effective equals the mean square displacement divided by 2 times t, with t being the number of time steps.
Right, divided by 2t. And just a quick note, the 2 comes from the dimensionality. Because it's a 1D line, you can go 2 ways, left or right. If this were a 3D simulation, it would be divided by 6t, because there are 6 directions, up, down, left, right, forward, back.
That's a great detail. But sticking to our 1D line, they run the simulation. 10,000 steps, 1,000 Kelvin, 1.2 EV barrier. They crunch the MSD, divide by 2t, and the final number the code spits out is 3.2 times 10 to the negative 7th meters squared per second.
3.2 times 10 to the negative 7th.
Now, I look at that number, and as a layperson, it's just a string of digits. Is that fast? Is that slow for an atom?
In the context of solid-state diffusion, that is absolutely screaming fast. Oh, yeah. For comparison, if you looked at self-diffusion in real copper at a comparable temperature, you might see a coefficient in the range of 10 to the negative 13th or 10 to the negative 14th.
Wow, so our simulation is orders of magnitude faster. Is that just because of the 1,000-degree heat?
The heat is a big factor, yes. But the biggest reason goes back to what we discussed earlier, the vacancies.
The 1,000 empty theater seats.
Exactly. We flooded the system with free volume. In a real solid, an atom might have the thermal energy to jump, but it has to sit there vibrating for hours waiting for a vacancy to wander by. In our simulation, there's practically always an empty seat right next door.
So the result, that 3.2 times 10 to the negative 7th, it's mathematically correct for the parameters we typed in, but it represents this supercharged, super diffusive scenario compared to a real hunk of metal.
Correct. It validates that the Monte Carlo algorithm works perfectly, but if you wanted to match a real-world experiment, you would just take that final number and scale it down by the actual probability of finding a vacancy in a real crystal.
Got it. Now, as we move into the outro here, I do want to do a bit of a reality check. I want to push back on the model itself for a second. We've been talking entirely about a 1D line.
The theater row.
Right. And the source explicitly notes this as a simplification. Real materials, real turbine blades, they are 3D lattices. Does flattening the universe to one dimension break the physics? Or is it still a valid approximation?
It's valid for learning the math and verifying the code, definitely. But you're right, it does miss some really fascinating physics that only happen in 2D or 3D.
Like what?
The biggest one is called the correlation factor.
Walk me through that.
Okay, go back to the 1D line. You are an atom, and you just jump to the right into a vacancy.
Okay, so now I'm one seat to the right.
And where is the vacancy now?
It's the seat I just left, so it's immediately to my left.
Right. Now, the computer rolls the dice for your next move. What is your most likely successful jump?
Well, the only empty seat is the one on my left, so I'm probably just going to jump right back into it.
Exactly. In 1D, you have an incredibly high probability of just reversing your last move. It cancels your progress out. Your movement is highly correlated to your previous movement.
Because the vacancy is trapped with me on this line.
Yes. But in 3D, the vacancy has way more options. After you swap with it, that vacancy might jump up or down or forward. It can literally escape from you.
Leaving me stranded in my new position.
Which is actually a good thing for diffusion, because the vacancy escapes. It allows you to eventually make a fresh move with a different vacancy that wanders by, instead of just bouncing back and forth with the same one.
So diffusion in 3D is actually, in a weird way, pure. Because you aren't forced into that annoying back and forth dance.
Pure is a good way to put it. The randomness is more efficient, but, and this is the crucial takeaway, the fundamental relationship holds true in both. The fact that the mean square displacement scales linearly with time, that is true in 1D, 2D, and 3D. The law of the random walk doesn't change, just the efficiency of it.
That's incredible. And I think that brings us perfectly to the real takeaway of this deep dive. We just spent 20 minutes talking about a Python script rolling virtual dice to move virtual atoms on a line. got a specific number out of it. Why does this matter so much?
It matters because we can't measure everything in the real world. Think about an engineer designing cladding for a next-generation nuclear reactor. That material has to survive intense heat and radiation for 50 years.
You can't put a piece of metal in an oven for 50 years just to see what happens to it.
Right, you'd be retired before the test finished. You can't wait that long. So what do?
You simulate it.
You take the known physics, the lattice structures, the migration energies, and you build these Monte Carlo simulations. You run them on supercomputers, and you can simulate 50 years of atomic degradation in a week.
But to rely on that, to build a reactor out of it, you have to trust that the simulations is basically reality.
And that is exactly what this technical lecture is demonstrating. It proved that by using simple random rules, literally just rolling digital dice against a probability formula, you can perfectly reproduce the exact macroscopic diffusion laws that we observe in the real world.
It bridges the gap.
It bridges atomic chaos to engineering reliability. It turns material science into a predictive field.
It really is a profound thought. I think we tend to view science as these very rigid, absolute formulas. But when you zoom all the way down to the bottom, to the atomic resolution, it's not rigid at all. It's a casino.
It's all probabilities and dice rolls.
But out of that microscopic casino, we get the predictability that lets us build skyscrapers and airplanes. The stability literally emerges from the chaos.
The law of large numbers at work.
Absolutely.
Yeah.
And, as we wrap up, it really leaves me with a provocative thought for you to mull over. If we can simulate something as physical and concrete as solid-state diffusion this accurately, just using simple probability rules.
What else is just a random walk?
Exactly. Think about the spread of a rumor on the internet, or how a virus moves through a crowded city, or even the stock market fluctuating day by day.
Are those just random walks waiting to be decoded?
Are we all just atoms waiting for a Monte Carlo dice to be rolled? Something to think about.
It definitely is.
Well, that wraps up our look at vacancy diffusion. It's a great reminder that sometimes to understand where things are going, you have to embrace the random walk.
And make sure you calculate your mean square displacement along the way.
Always. Thanks for taking this deep dive with us. We'll catch you on the next one.